trees are extremely important combinatorial objects, particularly in computer science. In this lecture, I'm going to introduce you to a little bit of tree counting generating functions using some of the concepts that we've learned earlier, namely combinatorial classes, isomorphism of combinatorial classes, and constructions involving combinatorial classes. But first, let me define what a tree is, and I'm sure most of you already know this. A tree is a simple, undirected graph connected without loops and no cycles. Okay, so for example, when I say simple graph, that just means that I am not allowed multiple edges between nodes, and I'm not allowed loops from a node to itself. So these are not allowed. So this here is a perfectly good example of a simple undirected graph. And this graph is even connected in the sense, given any two vertices, you can find a sequence of edges that will take you from one vertex to another. But this one is not a tree because there are cycles, namely this cycle here, this cycle here. You can go around without repeating any edges and come back to the same vertex. So this one is not a tree. But if I remove a couple of its edges, it will become a tree. For example, well, that's just even a line. Let's do something maybe a little more interesting. Okay, so that's a tree. And when I say a rooted tree, that means a tree with a designated vertex called a root, a distinguished vertex, which I'll call a root. The root. So let me just draw another slightly more complicated example. Here is slightly complicated looking tree, and I can take any of its vertices and designate it to be the root, and then this will be become a rooted tree. So this is the root. And once I have a rooted tree, I can draw it so that the root is, well, I guess you should draw it at the bottom, but I'm going to draw it at the top. It's an upside down tree. So I'll just redraw this tree. I have the root up here, and then from this root come out three edges. So I call these the children of the root. And each of these nodes here, which are adjacent to the root, again have children. So they are these three vertices, 1, 2, and 3. These are the children of the root. And this child of the root has 3 children of its own. And so I'll draw them in the next layer. And this child has 1 child of its own. And this child has again 3 children of its own. And none of these children of these roots have any further children. And so these branches of the tree stop here. These nodes are called leaves. So maybe I'll color them green. These are leaves. This guy here, I haven't finished drawing the tree. It has 1 more child. And that child is in fact a leaf. And here I have 3 more leaves. So here's the anatomy of a tree. This is the root. And these are leaves. All these. 7 leaves in here. And these remaining nodes are called internal nodes. Okay, so every node of a tree is either the root or an internal node or a leaf. In fact, the root we think of as an internal node. So let me just write this down because it'd be important when we're counting. Every node in the tree has a unique neighbor. So every node in the tree except the root has a unique neighbor that is closer to the root than itself. So I'll call it in the direction of the root. Which is called its parent. So these three leaves have this parent. This parent itself has the root as its parent. And the remaining nodes are called its children. And a node with no children is called a leaf. And a node with children is called an internal node. Okay, so let's just now try to count trees by their by the total number of nodes. So let T be the class, combinatorial class of all trees, and the size of T is just the number of nodes. So this tree here that I have drawn has 1 plus 3 plus 7 plus 1. Its size is I guess 12, because it has 12 nodes in all, and we want to count this thing. So I claim that T is isomorphic, this combinatorial class is isomorphic to X, the atomic class, which has one element of size 1 cross M set of T. And let me give you the bijection visually. So let me just copy out this picture. Now this is an object on the left hand side, and let me show you what it corresponds to on the right hand side. So I need to give atomic object, which I will just take to be the root itself, and then I need to give you a multi-set of trees, and that will just be coming from taking these pieces here. So this thing occurs, this is indeed a multi-set, because these two are really the same tree. It's a tree with a root, single root, and I should say here rooted trees with a single root and 3 children, which are leaves. So this is a multi-set of trees. So anyway, it's easy to write down formally what this bijection is. But what does it tell us about the generating function for trees? It tells us that the generating function of rooted trees satisfies the equation x. So I just write down the multi-set expression sum m goes from 1 to infinity tx to the power m divided by m. Now this is, I don't know how, I mean, a nice way to solve this, but certainly you can expand both sides and then solve for the coefficients of different powers of x, and thus get some sort of recurrence relation between express the number of trees of size m in terms of the number of trees of smaller size. Things work much nicer when we look at slightly simpler classes of trees. This is the most general class of rooted trees. And so let me now define a plane tree. A plane tree is a rooted tree where we care about the order in which the subtrees occur. So you could think of it as drawn on a sheet of paper, or the order in which by subtree I mean you take each node and you look at the tree that descends from it, and that you can call the subtree with that node as the root. So yeah, here actually these are roots of the trees, in which the order in which the subtrees occur matters. So if I were to take this example here and rearrange it a bit, I would get a different plane tree. So this, and let's just take this picture and do a little bit of surgery here. Maybe I'll just cut out this part and stick it, and cut out this part. Let's stick this here, and let's stick this. Over here. So now these are isomorphic as trees but not as plane trees. The same rooted tree but different plane trees. So now what we care about is the order in which these subtrees that are attached to any node occur. And so here what we get is, if we call T plane the combinatorial class of plane trees, then what we get is T plane is isomorphic to x times, and now it's not a multi-set, actually the order matters, so it's a sequence of T plane, a sequence of plane trees. So now the order in which these three subtrees occur will matter. So here I wrote them in any random order, these three things, but now it matters whether this came first, this came second, and this came third or not. And so what we get is the generating function T plane of x is equal to x over 1 minus T plane of x. This looks somewhat similar to the generating, the Catalan generating function had a certain recurrence relation. If I call this y, then what we see is y is equal to x into 1 minus y, which is the same as saying that y squared minus y plus x is equal to 0. And so solving using the quadratic identity, you get y is equal to 1 minus 4x to the power half divided by 2, which is x times the Catalan generating function. There we had divided by 2x, and here we just have divided by 2. And so we get this surprising relation that the number of plane trees with n nodes is the Catalan number Cn minus 1 for all n greater than or equal to 1. The last kind of tree that I'll talk about is a binary tree. A binary tree is a plane tree where every node has 0 or 2 children. So, for example, you start with a root here, and now this root can have 2 children or 0 children. Let's say it has 2 children, and this again can have 2 or 0 children. So let's say it has 2 children. Let's say this has 0 children and this has 2 children. This has 2 children, of which one of them has again 2 children, and let's say this has 2 children. So this is an example of a binary tree. And as before, we have leaves, we have the root, and the root and all the other non-leaves are the internal nodes. Now, one important point about such trees is that the number of leaves is equal to number of internal nodes plus 1. For example, in this picture, the number of internal nodes is 1, 2, 3, 4, 5, 6, and the number of leaves is 1, 2, 3, 4, 5, 6, 7. You can prove this identity by just seeing what happens when you add 2 children to any of the nodes of an existing tree. And so you can do it by induction. So for example, if I had this tree and I were to add 2 children over here, then this new tree would have one more leaf, because an old leaf has now become an internal node, and so it would have one more leaf than the old tree, and it would also have one more internal node than the old tree, because one of the leaves of the old tree has now become an internal node. So using induction, you can easily prove this, that the number of leaves of a binary tree is equal to the number of internal nodes plus 1. And I claim that this so let's define the class of binary trees. I just need to tell you what the size function is, and I won't take the size of all the nodes. It works out better if I take the number of internal nodes. So this here is a binary tree of size 6 rather than 13. Okay, and I claim that T bin is isomorphic to epsilon. This is the class which has one object of size 0 plus x cross T bin squared. This epsilon refers to the tree with just one node, which is the root, and since it's the root, but the root is also a leaf in this case, and so this just corresponds to this tree with just one node, which is the root. It has no internal nodes at all. And but the remaining trees which have where the root has 2 children are going to give us elements of x cross t squared bin. So if I take, for example, this binary tree, I can break it up. I get x, that just refers to the root, and then I need to give you a pair of binary trees. So I'll do what you would you're probably all thinking. I will take this subtree, this I will make the root, and this subtree here. Oops, I lost a couple of pieces of it. Let me just draw them back. So this is the element of x, and this is t squared bin. These are two binary trees. And so now what you get is t bin x is equal to 1 plus x times t bin x, the whole squared, which means that this was the same as the Catalan generating function. Which implies that the number of binary trees with n internal nodes is equal to the nth Catalan number.